about are challenges in image processing, or how do we turn those petabytes of mostly imaging data that we're taking into actual information, into something that we can do science with. And I know that yesterday we had some trouble reading the slides, so I put the slides online. They're on ls.st/0p2. Just a note that I hate fonts these days because in the good old days, 0 used to be crossed out, so you could tell it's a 0 and not an O, so I wrote it down here. So if you go to that address, you should be able to get the PDF of these slides. And if you can't, let me know. I'll fix it. Let me give you some of the context for this. So we, and I count myself into this, are used to doing analysis off of catalogs these days. So you go to an online archive, you download a whole bunch of measurements in a certain area of the sky or over the entire sky, and you use the magnitudes and error estimates that are in there, and you just simply more or less assume that they're true. You definitely do not think, how did those pixels get converted into magnitudes and error estimates? So that's a mystery to most of us. Yet science needs today push us towards things like measurement of subtle effects, so 10 to the minus 6 type things, 1 in a million. Ever higher precision. We used to be talking about a percent level photometry. Now we're talking about sub-percent level photometry. And then we have, at the same time that we want to push towards higher precision, we have ever more data. So that's usually incompatible with higher precision because more data means that you have to automate everything that you do, and you don't have time to manually intervene if something goes wrong to improve the precision, right? So at these levels, if you want to do this kind of, these kinds of measurements, what turns out to be crucial is really to start understanding the transformations from images to the actual catalogs of the measured data. And as I'll show you in a second, that turns into the understanding of our instruments. So what is it that our telescopes, that our cameras, and that our software does to these images as they pass through the pipelines and finally end up in catalogs? So that's the motivation for this lecture. So what I'm going to give you here is a fairly high-level walkthrough so you get a feel for how those images turn into catalogs. This will most certainly not give you everything you need to actually go ahead and do it yourself or even to understand the mathematical details of all of it. But at least I want you to know or hear some of the terms so you can go ahead on your own and go in depth into any one of these areas when the time is right. Let me begin with a little bit of an introduction. Sky maps and data rates. So this is one of the early sky maps. This is what I'm calling here an analog universe. This was made in the 50s. These are the so-called Shane-Virtanen counts. So this is using about 1,200 plates from the Lick survey. What they did was they, by hand, measured the galaxies down to about 19th magnitude, and then binned them, also by hand, into something like 1.6 million pixels. This is 10 arc-minutes by 10 arc-minutes pixels. The processing rate was such that the analysis took from 1947 to 1954, and actually the final catalog was published only in 67. So it took a while. 1.6 million pixels. Then we have, sometimes in the 80s, the arrival of a digitized universe. This is not digital universe, this is digitized. This is still, we have big photographic plates, but now we have machines that can actually go ahead and measure them. So this is a photo of a machine in Cambridge, UK called the Automatic Plate Measuring Machine, or APM. This ran on a 200 megahertz Pentium Pro. I think anyone here who has a smartwatch probably has a faster machine on their wrist at this point. And it took about 4 hours to process a plane, to process a plate. The sky at this point, you could measure it to 10 to the 12 pixels at 0.5 arc seconds per pixel. And then we get roughly in the 2000s, we get to a digital universe. And one of the, I would say, a good example of this change and the harbinger of a lot of these things that have come since was the Sloan Digital Sky Survey. These are big mosaic cameras. This is the SDSS camera. The sky can now be covered with something like 10 to 11 pixels. Processing rate at that time was 4 megabytes a second, if you look at how much of the sky we were really downloading. And it took about, for Sloan, it took about 200,000 lines of code to process it. So this is a point where we really are starting to get into software as being one of the key things in measurement. We're not talking anymore about thousands of lines of code, but hundreds of thousands of lines of code. And so in the next decade, I showed you yesterday the LSST. So LSST is going to take this up to the next level. And with LSST, you'll see that soon, the data rates are going, again, significantly higher. But also, the numbers of lines of code are going significantly higher. The complexity of how we process information to go from images to catalogs is growing. Here's the LSST camera, 3.2 gigapixels. These are CCDs that or CCD devices that are what it's called deep depletion devices. They're thick devices. I'll tell you in a minute why that's important. But this is, I think, the interesting number. So remember, in the case of SDSS, we had about 4 megabytes per second of processing rate. Here we have 170 megabytes a second. So it went up a factor, more than a factor of 10. And the number of lines of code is 1.1 million. And actually, by the time we get to the finalized code base, the number, that line of code count is going to go up to about 2.5 million. So we're getting to a place where we're now going to have, quote unquote, a big data universe. This is an example of what a single chip of an LSST image looks like. This is actually a simulation. Each exposure is going to have 189 of those, and then we're going to tile the southern sky with those exposures. So that is what's represented in the bottom, on the bottom here. So what we want to do is we want to take those images, and as pretty as they are to look at, we just don't have time to go look through all 5 million of them. We want a computer to look at them. And in those 2.5 million lines of code, we want to have the logic or the algorithms for the computer to go and detect and measure things that we find interesting and that we care about on those images, so that we can focus on the things we care about and ignore the noise and things we don't care about. So I'm going to ask the audience here, because I think most of us are astronomers, what do astronomers care about in an image? So here's just an example of an image. Anyone wants to venture a guess?
Flux.
Say it again?
The flux of the
Flux. What else do we want to know? Positions. Say it again? Correlations. So say from between fluxes of different objects or positions and shapes, structure, shapes.
What response function of the detectors, and also like what type of light are you observing? Is it X-rays or?
So we want to know all of this as a function of wavelength, right? So yes, one of the things we want to know is what is on the image, right? There are stars, there are galaxies, there are other objects. Where is it? So we want to know where is it both relatively. I want to know how far apart are these two stars, especially I want to know whether that's changing. I want to also know it absolutely. This is where Gaia is unsurpassed. Where exactly on the sky are things? How bright are things? So that's the flux. Is the flux changing in time? There's this whole new area of time domain astronomy because we know, although the sky looks pretty static, it actually isn't. Is it moving? There are things that not just change the sky, but move. And what is its shape? And this question can be posed in two different ways. One is, what is the shape of a particular object? Say if you're looking at an interacting galaxy, you want to understand something about merger processes, or statistically for a class of objects, if you want to understand the nature of dark energy. For example, you don't care about the measurement of shape of any particular object, but what you do care about is for a whole group of objects in a certain area of the sky, are they all systematically sheared in a certain direction relative to others? And those are two different measurements. Okay, so we want to learn all of that from images, and we want the software to tell us that. So to do that, we need to understand a little bit of how astronomical images come to be. So here's an astronomical image. This is from the Good South field. This is a deep VLT stack. And I'm going to zoom in on one small portion of this image. And so we have looked at this for so many times that we don't notice anything strange in this image. If you knew nothing about astronomy other than that there are stars out there and galaxies, let's just think that there are stars out there. One of the things that you would find odd is that stars are supposed to be really far away, yet this here is a sizable blob, right? Why isn't this a point? And we know that this isn't a point because there's something called the point spread function. There's the light coming from the star doesn't go directly into our detector and hit exactly the same spot in the detector, but things happen to it, either passing through the atmosphere or through a telescope and so on, that create these kinds of blobs. And when we measure the light or the position or the properties of stars, we need to take all those effects into account. So to be able to take them into account, we need to understand exactly what's happening. So here, what I'm showing you is a simulation, in this case the LSST, but you can do this for many telescopes, is a simulation of photons raining down from the universe onto the atmosphere through the telescope, so bouncing off of our 3 mirrors, into the camera. These are the lenses of the camera. Then into the detector, which is up here, so photons are blue. They get into the detector, get converted into electrons, and electrons drift through the silicon of the detector, and we get our image up here. So the poor little photon has to go through all of this to finally get counted and turned into an image. So this will restart. Let me restart it once more. The interesting thing here is that as the photon travels and does all these bounces, etc., its direction can change. So here you can actually see it in the atmosphere. It's been intentionally exaggerated. Some of these photons kind of go in slightly different directions and do this. Whenever it hits a mirror, it can actually bounce slightly, again in a slightly different direction than it would for a perfect mirror. When it gets into the detector and gets converted into electron, it's supposed to travel on a straight line, but it doesn't. It's guided by electric fields, and that doesn't have to be straight either. And it's a combination of all of these effects that turns our perfectly point-like star into a blob that looks like this on the detector. So you can actually go ahead and quantify all of this. This is something that I find interesting that we haven't really done this very much in astronomy until recently. If you look at particle physics, when they build detectors, they do all kinds of simulations like the one I just showed you to understand the performance of the detector even before any first piece of silicon is built. Whereas in astro, we are kind of more of a, we're a little bit more in a Wild West situation where we kind of say, we want to build a 5-meter telescope. Let's just build a mirror, put it in the sky and see what happens. It worked well up until some point, but now we need to start doing the simulations and understanding things at a much deeper level because of all those things I said in the introduction. So if I take that simulation and I start looking at how the photons of an individual point source get moved around, I can actually compute, or I can predict, the different effects that are coming from the optics. So I take a perfect point star, it passes through the telescope, And just because of the imperfections in the optics of the telescope, it's going to be spread out into something like this, right? Hubble Space Telescope, if you're using a space-based telescope, these are the kinds of things that are actually going to be, this and a few more others in here are going to be dominant in your point spread function. Then the telescope is not tracking perfectly. There's also diffraction. Then you cannot align every single lens and mirror perfectly. So you get effect due to that. This is detector misalignments. These are lens misalignments, mirror misalignments. Then you have a detector which is not perfect, your silicon. And then all of that turns out not to be important if you're on the ground, because on the ground, the atmosphere is the worst. So here's your high altitude atmosphere, which is fine. Mid altitude atmosphere, which is worse, but still fine. Low altitude atmosphere. This is really the thing that kills you. And then on top of that, your detector has finite pixels and you have pixelization. And then if your star is really bright, it saturates, it blooms, and you get the image that looks like this. So this is how images are created. And so our challenge, or the challenge of the software that we have, is essentially to go backwards, to start with this and to infer what was the brightness of the star here, so even before this point. So how do we do that? Typically, this entire complicated process, we ignore all the details and we just approximate it by saying, I have a point at the beginning, and that point gets turned into this big blob by an operation that's effectively convolution. And a convolution by something called a point spread function. So basically, I have a truth image that's up above the atmosphere. I convolve that truth image with the point spread function. Point spread function is how a single point gets spread out. And then there's some noise. And the noise comes from either Poisson noise, because the photons are quantized, or more likely sky noise, which is the dominant noise in virtually all kinds of observations. Yes?
The truth would be in the last slide would be the optics one, or?
No, the truth will be above the atmosphere before the optics, before anything. So it would be just a point with a certain brightness at a certain position. So I have PSF that convolves my truth, and I have some added noise, and that's my observed image. And so my challenge is to try to go back from there. Yes?
How about extended objects?
The same thing works for extended objects, because this truth image, you can think of that as a scene on the sky that's infinitely well pixelized, right? So your extended object would be extended, but still convolved with the point spread function.
My point is that you know what a point looks like.
Mm-hmm.
So you know the truth value of a point spread function. But for an extended object, we don't actually know the truth of an extended object.
We don't know the truth for any of these objects, right? That's what we're trying to infer.
A star is a fairly good approximation of a point.
Right.
Because it's so far away that it comes to the point of the extended object. Like my point is that we don't really know the truth value for an extended object that we do for a star.
So for an extended object, I think what you're trying to say is that for a star, we have a good model.
Yes.
We're basically saying that this is a point source, whereas for extended objects, if we try to model it with something, it's not clear what we would model it with, which is true. Let me get to that in a couple of minutes when I discuss how we do models with that. Okay, so if you look at this equation, there are two things that we want to know. Well, there's one thing that we want to know, which is truth. But to get to the truth from the observations, we need to understand something about the noise, and we need to understand something about the point spread function. So we need to estimate the point spread function. How do we do that? This is what's typically being done today. We try to estimate the point spread function from the data, because we know there are points in the data that are just been spread out by the point spread function. Those are bright stars. So we find bright stars, or our software finds the bright stars, And then if you zoom in on those bright stars, or I should say bright objects, you try to detect which one of them are extended because of just the point spread function, and which ones are actually likely to be extended by themselves because they're galaxies. So here's an example of something that's a galaxy. You throw that out. You keep only the things that are consistent with stars, and then you have a realization of the point spread function at every position in the image where you have those stars. Now the problem is that you typically want to measure, say, here, or you want to measure this galaxy down here. So you need to find a way to interpolate. This is what we've done here was we just sampled the point spread function. Next thing we do is we model it. So I can take one of these stars and I can say it's a combination of some basis functions. Typically, things like Gaussians are used, or something more complicated like a PCA decomposition. And then some interpolation scheme is utilized to, in essence, go from, I know the point spread function here, here, and here. What is it here? And the interpolation schemes are fairly simple. It's like Chebyshev polynomials over the image or something similar. As you can tell, I'm skipping a whole lot of detail here. I don't really have time to go through the math. The reason why I showed you this is to try to get us to think how we can do this better. Because I showed you all those simulations and how the photons are raining down and the simulation of what's happening in the optics. And I actually haven't used any of that to do this estimation, right? So effectively, I'm throwing away information. So can we do better? The answer is yes. Because the PSF is a combination of two effects. One that is deterministic, which are things like how are your mirrors misaligned? How is your detector manufactured? That you can measure in the lab, or that you can measure, characterize in the dome. So in principle, you should be able to pre-compute this effect, 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 all the way to there. And then these pieces that come from the atmosphere changes all the time. So you cannot pre-compute what the atmosphere is going to do, but you can constrain it because the atmosphere doesn't change in absolutely any way, right? It would be very unlikely that the atmosphere, that in one part of the image you have a point spread function that is almost a perfect point, and right next to it, it blows up, right? Because that's just not how the atmosphere works. The atmosphere has winds. They move at a certain velocity. They move in a certain direction, and so on. You can actually show that the power spectrum of fluctuations in the atmosphere to first order is a Kolmogorov power spectrum. It's turbulence. So you can use that to constrain what these stochastic effects look like. And you take all of those things into account, and you actually get PSF estimates that are something like factor of 2 better. So again, a lot of hand waving, but this is the kind of thing that was actually done only in the last couple of years, in the last, I think, 2 or 3 years. Question?
I would guess the PSF is also dependent on wavelength.
Yes. Give me 10 minutes. I'll get to that. So this is the first improvement we can make in computing the PSF. But then you discover that as you start delving deeper into how images get formed, then you discover that things are not as simple as you would hope. Here are 2 images from 2 different detectors. This was in Pan-STARRS. That one over there is DECAM. So this here are astrometric residuals computed over many, many exposures of DECAM camera. And note that they're not random, right? This is not random at all. These here are photometric residuals over exposures, computed over many exposures of the Pan-STARRS camera. They're not random at all either. And look, they're at a level of 1 or 2%, and we're trying to get to sub-percent photometry. So this is what's been discovered actually for the first time in LSST silicon back in 2014. And this is what people have started calling tree rings for obvious reasons. Who here ever thought that they would be learning solid-state physics to be an astronomer? How are chips produced? How is silicon produced? The sound is not that good.
This is the raw material chips are made of.
Sand.
Sand. It is made up of silicon dioxide. Silicon is the second most common element on the Earth's crust.
Thank you, we know that. So, this is the important piece of this video that I wanted to show you. The silicon that we get for CCDs is basically the same silicon that is used to manufacture chips. The way it's manufactured is by taking a whole bunch of sand, melting it, and again, I'm oversimplifying a little, putting in a big rod, and starting to spin that rod and starting to take it, and then taking it out slowly. And as you do that, this, what is called the silicon bulle, starts growing as more and more silicon gets deposited on the edges, and it grows, 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 you get the whole thing out. Now the fun thing is that the rate of growth and impurities is super dependent on things like humidity, temperature, you name it, any kind of process. And it takes time for them to extract one of these silicon bulles. And any kind of impurity or density any kind of impurity or density variation that you get in that silicon turns into, when you add electrodes to the silicon, turns into essentially parasitic electric fields that are parallel to the growth rate of the bulle. So what you get is you get photons hitting the detector on top, starting to go down, drift towards the bottom. Remember that simulation that I showed you. But because the density here and density here is different, because maybe humidity was higher yesterday than it was today, some of those electrons are going to be systematically pushed in one direction versus another direction. And the consequence of that is that more of them perhaps end up in this bin or in this pixel than they do end up in that pixel. And what you get, and that's an effect that's radially symmetric around the center of how that silicon bulle was growing. And what you get are tree rings. You get these kinds of things. So this is basically photons being redistributed in detectors. The fun thing is that we've been using CCDs for the past 25 or 30 years, and we didn't know about this until about 4 years ago. And this is a 2% effect in some CCDs.
Excuse me a question.
Uh-huh.
Why is not this effect readout because we're using a flat image?
Flat makes it worse. Flat fielding assumes that it's a quantum efficiency issue. So flat fielding assumes that for some reason the photon entered the pixel and then it disappeared. It wasn't recorded as an electron, right? The quantum efficiency of converting a photon into electron was worse in this pixel than in an adjacent one. Whereas what's happening here, the photon didn't disappear, it just moved to the next pixel. So you're misinterpreting what's actually happening. Your charge is conserved and you're thinking it's not. So you're overcorrecting one pixel and you're undercorrecting the other. When you do the math, you realize that flat field actually makes things worse at these levels. So that's another reason why, another reason why it's important to understand the physics of these things so you can properly do the corrections. Otherwise, you end up doing the wrong thing for about 20 years. Then, as we started looking, or as you know, the community really realized that these devices are more complicated than thought, other kinds of effects started showing up. Here's another one. So these are the heights. You don't really think about it that much, but these are the relative heights versus width of pixels in CCDs. So this here is the Hypersa PrimeCam camera. It's one of the biggest cameras, optical cameras that we have today. And this here is just to make things cute. These are the tallest buildings in the world. So it gives you a feel for the aspect ratio. So HSC pixel is a skyscraper, and LSST pixel is also going to be a nice skyscraper. Your photon flies in from the top, gets converted to an electron somewhere around here, and then that electron starts drifting all the way to the end and being pulled by the electric field all the way down. this is tall. There's a lot of time for things to go wrong, right? What kinds of things can go wrong? One, we've already seen, the brighter, fatter, but the tree rings, right? It can get pushed out into the adjacent pixel. Another thing that can happen, which wasn't also quite understood until recently, is what happens when you start filling up this pixel. So each pixel can contain, an order of a couple 100,000 electrons before it gets overfilled and saturates. We know what saturation is. That's when you get those nasty spikes in the image, and that usually ruin your day and all the objects that are underneath the spike. Well, turns out that things happen way before that, because let's take a look at what happens when your pixel is half full. What does it mean that a pixel is half full? It means that the electric field, you start with your pixel being on some electric charge that pulls the electrons from top to bottom. It's usually something like negative 40 volts or something like that. But when the pixel is half full, that means that you have enough electrons down at the bottom to generate the opposite electric charge. So your effective electric charge now is not minus 40 volts, it's minus 20. So that means the next electron that comes in here doesn't feel minus 40, it feels minus 20, which means it drifts more slowly downwards, which means it has more time to, say, drift into adjacent pixels for any impurity or anything like that to push it aside, because it doesn't feel really strongly pulled downwards. And it turns out that we see that the brighter the pixel is, the more you see that the photons are leaking out of it. And that's what's being called, for that reason, the brighter, fatter effect. So the brighter the star is on the image, the fatter it's going to look like. This is also at a level of 1% or 2%, depending on the detector. And this is also a thing that wasn't understood until recently. So we had these, when I was in school, they told us, CCDs are awesome. Unlike photographic plates, they're linear. You can think of pixels as photon buckets, and every pixel is independent. You don't have to worry about what this pixel does and the one next to it do. They're all independent. They're not linear. They're definitely not independent, because these electrons flow all the way, all over the place. And these are all effects at a level of 1% or 2% that we care about if we want to understand dark energy or if we want to do photometry at sub-percent level. These are just the two that we understand now. I bet there are more that haven't been understood. So these are the kinds of things that some of you might encounter and have to figure out to get your science done ultimately. Okay, let's say I find a way to correct for all of those effects, and there are ways. How do I actually go and do the measurement? So this is where we're going to get into the question of how do we model galaxies. One thing we could do is deconvolve, right? So I estimated my PSF. I now understand all of those effects. So I know what my PSF is at every point in image. Why don't I just take that and deconvolve? Well, the answer is this would not be easy because of the noise term. So deconvolution without regularization would amplify the noise a lot. And then any errors in the estimate of the PSF will be further amplified in the deconvolved image. So there's a lot of literature on that. I'm just going to state that without proof. So instead what we do is we effectively do regularization by saying that we do not want to directly deconvolve the image, but we're going to model the scene that's above the atmosphere as a composition of objects that are at fixed points, fixed but unknown points. And those objects can either be stars, which are point sources, or galaxies. And I'm going to take the sum of those models, and I can convolve the sum of those models with the PSF. I can add the noise, and that's what my image is. So I'm going to model the entire universe as consisting of stars and galaxies. And then for galaxies, I'm actually going to say, well, galaxies are all actually really simple. All it takes to describe them are two exponentials. Or actually a little bit more generalized. So an exponential plus a Debye-Coulomb profile, you can think of it that way. So here's an example of a galaxy that looks just like that. Here's the galaxy. If I only model the bulge, I have some extra flux in here. If I only model the disk, I have extra flux. If I model it as bulge plus disk, it is gone, which means I got the correct model. So the idea is you basically run a modeling loop. You assume that there are stars and galaxies in certain positions in the image. You convolve that image, those positions of those stars and galaxies with the PSF. You then take that fake image, in effect, subtract it from your real image and compute the chi-squared. And you go back. And you run this loop, you tweak the positions of objects, you tweak the parameters, the fluxes, or the shapes of the galaxies, and you run that until you get something that's close to optimal. Question?
How do you deal with degeneracies in the model?
You don't. You record them in the covariances. So your covariance matrix is going to show that certain parameters are going to be degenerate. Or more generally, posterior distributions, and we'll get to that. Yes?
The effects that you were describing, I mean, this drifting of photons,
Mm-hmm.
cannot be included as a PSF, right? So you have to do something else to deal with those.
Yeah, there are, so the way we're correcting those effects right now is at a pixel level. Turns out you can correct about 90% of it by essentially running a kernel that's not quite a convolution, but running a special kernel over the image that redistributes that charge back. And then you treat the rest, and then you pretend that you've taken out all of it, and then run the old PSF procedure. It's something that is approximate, and I hope someone will come up with a better method, but we don't know a better method yet. So this loop is how your survey data gets built, all right? So this should already, I think, be eye-opening in a certain way, because this already tells you that if your galaxy is more complex than a double exponential, its flux measurement may not be as accurate as you think it is. But this is how things are done. So this is one of the caveats that I wanted to bring up here. Understand those magnitudes that you have in catalog. Understand how they were derived. In SDSS, in LSST, in PanSTARRS, in virtually every survey, this is how they do it. So that means that for small galaxies, small faraway simple galaxies are going to be almost perfect. For stars, they're going to be perfect. For things that are extended, that show structure, not so much. So if you see some interesting signals in those kind of galaxies, it's probably this. It's probably not some interesting signs that you found. So then you take a look at what we've done, and you realize one thing. If you look at this from a point of view of a computer scientist, if you look at this from a point of view of an astronomer, what we're doing is we're decomposing and modeling the sky in a way that makes physical sense. So what that means, we take this image of the sky and we say we're going to decompose it into stars and galaxies, and we're going to model their positions and shapes, and that's what's going to be our sky. But if you're a computer scientist, you're going to take a look at that and say, oh, you built a lossy compression algorithm. Because this image here is not the same as the image in the previous slide. Right? Let me shift them back and forth. This is the real thing, and this image here is what I've reconstructed using just the catalog and the point spread function information. So I can take the catalog, I can put down my points and my galaxies, convolve with the point spread function, and look at how close they are. It's actually pretty good, right? But from a CS point of view, this is lossy compression. Lossy compression with a very physically motivated, I would say, set of models. There are challenges to it, and you mentioned one, which is that our model space is incomplete, right? We pretend that stars are point sources and that galaxies are double reciproc profiles. How do you describe something like this in that case? The answer is you don't. How do you describe something like this? This is from the DECAP survey. This is the center of the Milky Way, basically, or deep in the plane of the Milky Way. There are all these dust lanes that we just missed, that we Best case scenario model as the changing background. But worst case scenario, they're just missed and they're biasing the measurement of individual stars. So I think there's a lot of work to be done in, for these next generation surveys in understanding of how do we model these kinds of structures, things that are not what I call localized. So they're not galaxies that have nice and easy shapes, or they're not stars that are just point sources. So this is one of the things that I think is an open question and a challenge of what's the best way to do this sort of thing. Okay, so let's go beyond a single image. Everything I talked about so far deals with, we have a single image, we want to understand what's in that image, we want to measure the fluxes and positions of the objects or shapes. Your typical survey of the future is going to have hundreds to thousands of images of every position in the sky, and that's kind of what's shown here for LSST. So if you have multi-epoch imaging, what can you do with that? You know, generically, you can do two things. You can try to go deep. You can take all the images taken in a certain region of the sky and try to add them together to simulate one long exposure and see what's out there at faint magnitudes. Or you can try to see what's changed. You can take two images of the sky and subtract them and see what's different between the two images. So I'll go quickly through both of these, and let me start with image differencing. So image differencing is subtracting. Why do we want to do that? Why subtract? Here's an example of a not so crowded but relatively crowded field. And there's a star. There are a couple of objects in here that are new in one image relative to the other. There's no way you're going to tell me which ones. But if I do this, which is a subtraction, there are many artifacts, and I'll get to that in a second, but note, see these black points? Those are all the new things that were in one image and that were not in the other. If I zoom into one of those, here's a galaxy, here's a small galaxy, here's that same galaxy in the second image. You can kind of tell that something's changed. You can tell that there's a change in flux. But actually, when you subtract them, you find a nice point source right there, which is a supernova. Good. So we can align, subtract, profit. Everything is easy, right? Wrong. Because of the atmosphere. Every time you think you're going somewhere in astronomy, then the atmosphere screws things up. You can have one night an image like this, and another night you can have an image like that. If you directly try to subtract the two, that's going to result in something horrible. Even the number of objects is different in two images. What you need to do is, the difference between these two is seeing, is how good the atmosphere was in the first night relative to the second night. What you need to do is somehow get these two images to look as similar as possible. And this is what an algorithm called Allard-Lupton does. This was invented some 20 years ago by Allard and Lupton. And basically the idea is that I may have image 1 and image 2, and what's different between the two images is the PSF. The PSF is mostly, as we've seen in that simulation, determined by the atmosphere. So the atmosphere may be changing, the weather is worse one night, the PSF is worse. How do I convert one image so that it looks as well as the other image? Well, their answer is there's some kind of a convolution kernel that they call kappa, with which I convolve my, in this case, second image. I find that convolution kernel to essentially minimize this difference, to get a difference image that's as minimal, that's as small as possible in the least square sense. And then any actual differences that remain are going to be due to real differences, real objects that have changed position, brightness. And there's an algorithm how to find this convolution kernel kappa. Usually it's expressed in some kind of a Gaussian basis. I'm not going to go through all of that. And it generally works well. But it assumes a couple of things. It assumes that you have two images, one of which is in essence perfect. It's called the template image, which has very little noise relative to the science image that you're trying to difference. And that's, if that's not true, then effectively you end up in a situation where you're doing a deconvolution that amplifies the noise, and that is bad. Recently, there was another algorithm that's you can think of it as a modification of Lupton and Lord. Look at the paper by Zakei et al. 2006. We call it ZOGI, after the first authors, Zakei, Olfek, and Galliam, which showed that you can actually show that there is an optimal way to do this differencing, irrespective of what the PSF is on the first image, or what the PSF and noise are on the first image and the second image. And this algorithm right now is running on ZTF, and it works really well. But even when it works really well, things are complicated. Just as in the first example, the better you get the algorithm to work, the more other things you discover. So in this case, I'm showing you some image subtractions from pan-stars. In the real world, image subtraction turns out to be far from perfect. There are all kinds of artifacts you start seeing in those images that are due to the camera, due to the telescope, due to many other things that sometimes you can't influence. And the scary thing is, even with all the improvements in algorithms, typically we see somewhere between 100 to 1 to 10 to 1 false to true detection ratios in image differences. So in essence, you find things that look like this that is obviously not a real object. It's an artifact because the two images weren't aligned well. So these are kind of various reasons why that might happen. So why or how do we deal with this? This is, I think, I don't know, people may disagree, but to me, this so far has been the most compelling application of machine learning in astronomy. Because the way this was dealt with on PTF, which is a precursor to ZTF, was by applying machine learning algorithms to images, teaching them what a false positive looks like, what an artifact looks like, and what real objects look like. Essentially what stars look like, because most of these objects are star-like. And you run your machine learning classifier, and now in the industry, these are commonly known as real bogus classifiers. They differentiate between real objects and bogus objects. And you go from, here's the most recent example on DECChem, you go from 40 to 1 ratio of false to true to 1 to 3. So you suppress, you essentially invert that ratio. You get for every 3 objects that you see, for every 4 objects that you see, 3 are real. That's kind of what this is showing. So that is I think, wonderful example of an application of machine learning. And it's also a perfect example of what machine learning is good for, right? Because it very much, these are very much things that if a human looks at them, they could easily tell what it is. And to first order, all these, the machine learning methods, the deep learning, et cetera, if there's something that a human is good at, that's usually something where you're going to be able to replace a human with machine learning. When I say human is good at, it's human is good at by looking. Okay. A complaint about this is that we have taken a hammer to, if you have a hammer, then everything looks like a nail. And the group that did this had a machine learning hammer, and they applied it very successfully. But part of the reason why these images have so many false positives is because just the algorithms to do image subtraction weren't sufficiently good for them. So even with all the applications. So one way to do it, the way you can see this is if you look at these artifacts, the reason why you have this artifact here, one part is white, the other one is black, is because this star hasn't been properly aligned in 2 images. So if they're slightly offset and you do a subtraction, one side is going to be positive, the other side is going to be negative. So instead of unleashing machine learning to tell us about this, why don't we just fix the algorithm that does these offsets? Why don't we just understand why do we have these offsets and fix the algorithm? So this is something that people are actively doing now. So ZOGI algorithm is one of the attempts of that, and it's already improved things a lot. It went from 100 to 1 to something that's closer to 10 to 1 in terms of false to real ratios. And then there's some work on the LSST side to understand how to do this to to understand why this happens in telescopes in general, and how to fix it for future missions such as LSST. Now, because of time, I'm going to skip over some of this. Let's see. No, actually, I think I have 5 more minutes. Is that right?
Yeah, you have 5 minutes.
Okay. So, all right, let me show you just this thing. Option 2 is to understand the root causes of how this happens. And one of the reasons why this happens is, again, because we have the atmosphere, and the atmosphere refracts in addition to spreading the light out. And the atmosphere refracts light, so bends light differently depending on what your wavelength is. So whether it's a blue light or whether it's red light. If it's a blue light, it's going to be more affected than the red light. So what you might get is something called differential refraction, so something like this. If you have an object and you're looking at it at the zenith, and if you, this is right now I'm imagining that my CCD is just one-dimensional because I'm not good at thinking in more than 1D. So imagine that this here is an object and this is my one-dimensional point spread function. So here's the object and it's been spread out by the atmosphere a bit. When it's in the zenith, all different wavelengths of the atmosphere, because it's essentially just light raining directly onto my telescope, there's no refraction to them at all. So they all end up in the same position. If it's slightly off zenith, then basically the atmosphere serves or works as a prism. So light that is redder is still going to continue roughly on the same path, but light that is bluer is going to be bent. So I have redder light that still ends up in my central pixel with slight spreading due to the PSF, but I have bluer light that has now been bent and shifted a few pixels away, also slightly spreaded, and I have some light in between. So I add all these together, and this is now what my object looks like. It has 2 effects. 1, it's been shifted, and 2, it's been broadened, so relative to this. And you can imagine if I take 2 images, one taken in the zenith and one taken off axis, of exactly the same object, so nothing has changed. And if I just subtract them, I'm going to get a dipole like that, like the one that I showed you previously. So this is going to be over-subtracted, this part is going to be under-subtracted. So this is basically what happens here. The root cause of this is that the band pass is not infinitely narrow. So the light that comes down has different wavelengths. And so here's an example of a G-band pass. Here I zoomed in on it. And basically, all the light that's coming from this part of the band pass, may wind up in those pixels. So this is the red part of the band pass. From the center is going to be shifted slightly, and from the edge it's going to be shifted even more. So this is also a hint at a solution, right? Because if we observe, let me skip over this. If we observe the same object at different air masses, which means it's essentially different inclinations relative to the zenith, that same object, if we observe 2 different objects at different air masses, they're going to be shifted differently depending on their color. So here's an object that I'm going to call red. That one gets shifted. So this is that object seen in the zenith. This is slightly off. This is at very low elevation. So it gets shifted by a pixel kind of between these 3 positions. Whereas if I have an object that's very blue, it gets shifted more. So the idea here is I go and observe at various elevations, and I look at how the objects get shifted at those elevations. And from there, I basically infer what the color of the object is, because the blue ones shift more this way than the red ones. And the fun thing is that works. Once you do that, you basically have not one template image, but multiple template images within the band pass. This is the scary math. And all those dipoles go away, all the dipoles that are being caused by differential refraction. And you get an interesting byproduct off of this. which is you've effectively measured the flux of that object at 3 different points within the bandpass. So you typically, when you have one filter and you think, I have one filter, I can only measure, say I have a V-band filter, I can only measure V-band magnitude. Well, it turns out this actually gives you more information. It gives you information on what the magnitude of that object is on the left edge, in the center, and on the right edge. So that's what this plot shows. This is a simulation. These are the true magnitudes, and the pluses are the estimated magnitudes, and it's actually pretty damn good. And so you can then take that and create a kind of a false color image of your scene that's been taken with one band, right? So this is like measuring colors with one band and using the atmosphere as a prism to shift your band around a little bit. So to me, this is one of the coolest things I've seen in a while, because it's like getting you more information than you otherwise would. I'll skip this part to get to the conclusion. So I wanted to walk you through a couple of things here to give you a feel for what image processing looks like and how those catalogs come out. But I also wanted to show you that there's a little bit of a theme in all of those different examples. And that is that every time we dig deeper into understanding of instrumental effects and what is it that we're actually doing rather than just blindly, counting how many counts we have in pixels and adding them up, we discover something new, and we discover something new in a way that allows us to get more information out of the same data. So in the case with the PSFs, we discovered now that we understand how PSFs work, we can actually improve flat filling by a factor of 2. And that means improve photometric precision by a factor of 2. In the case of solving differential chromatic refraction, we'll actually discover that we can measure the fluxes of objects, or the difference in the flux of objects within the same band by using the atmosphere as a prism. And then the example that I didn't show you that involves with optimal with coaddition, we can actually measure proper motions of objects if we do something called multi-epoch fitting. We can measure proper motions of objects that are not even detectable in single images. What all this does is it shows us that we already have data on disks that contain more information that we're extracting. And basically, most of the information loss that we think of when we think of, say, oh, the seeing was terrible, and therefore I cannot measure to better than so-and-so precision. Well, most of that comes from the poor measurement method, because the information is still there. It's in the shape of this PSF, it's in how broad it is, it's in how correlated it is to the PSF around it. So we have better methods with exactly the same data, we can extract much, much more information out of it. And all of these are examples of that. And so this is really where you come in, because this is the kind of thing that's already started to happen. Here's the difference between Slow Digital Sky Survey data release 5 and data release 12 in photometric precision. So it was 2%, and I'm sorry I don't have these in exactly the same form, but it was 2% at DR5, and at DR12 it's 0.8%. So that's in a single band that's better than a factor of 2 improvement. If you look at that as in terms of colors, all those improvements multiply. So it's improvement of something like a factor of 16 in the ability of placing a point into this multidimensional color space. And all of these improvements came back from better understanding of the instrument. So as we're thinking about what the next survey is going to be, LSST already costs $1 billion, right? The next machine might be pretty costly if you wanted to build something bigger. So the next gen survey may actually be improvements to the software. If you take the same data and combine the data from different surveys and properly measure it, you can get improvements of factor of 2 or more with exactly the same information. And we're starting to see that more and more and more. So that's why things that we're learning here are going to be important, because maybe in 2030, that's how we get to the next big discovery from the same data but with better algorithms. All right, I'll stop there. Thanks.
So we are already at the coffee break
You do, so, but you have, those changes that will tend to spread out or change the size of the PSF mostly. They will not tend to, they will not essentially change that much the index of refraction of the atmosphere, which is what gives us the information here about the color.
There was another question there.
So we now have a lot about how the atmosphere messes up our vision. Is there any reason not to go to space other than money?
Space is difficult. Even if you had infinite money, something goes wrong in space, you cannot just go send someone to fix it, right? And that's partly why it costs so much. So there are logistical reasons to build things on the ground if you can, but to be honest, money is a pretty good reason, right? LSST is 600 million, JWST is, what is it now, 8 and counting billion?
The light gathering on the ground,
Yeah.
you can build bigger stuff on the ground.
Yeah, but I mean, I'm trying to come up with a way not to involve money because you can theoretically, with infinite supply of money, you can build a 100-meter telescope in space. But yeah, but I think logistical issues of, everything has to work, otherwise you're delayed by years. Yeah.
I
Sorry.
think we can stop here and come back.
I'll be at the coffee break. You can ask me questions. All right, thanks.